So I just made a sundial. Here is it at 11 o'clock, and here is it at 12 o'clock. So you know it works. If you want to argue against me, make your own and show me how you're going to do it. But I want to show you why it works on flat Earth and how sundials just work in general. There's a few different types of sundials. The one I'm talking about is where we point it to what's called the North Celestial Pole or the South Celestial Pole. So a lot of you may be familiar with these domes within a dome. On the flat Earth model, our individual perspective is presented as what's called the celestial sphere. These are well-known astronomical concepts. You have your right ascension and declination, and right ascension is pretty much this circle part right there. Depending on what the right ascension is, the sun will be at some different part of that circle, and coincidentally, right ascension is actually measured in hours as well. But what you have to do, though, is you have to point your stick towards Polaris, which is also the same thing as the North Celestial Sphere. So depending on where your latitude is, for example, I'm in Belize, our latitude's about 17 degrees, that means my stick has to be pointed 17 degrees from the horizon, just like you see in this photo, and directly at the magnetic north where your compass is pointing. Not the geographic tourist spot where you can go to take photos. You need an actual compass to point to the real magnetic north or your sundial won't work. You'll know it works at 12 o'clock if the sun is directly under the stick. That's an easy way to know if you did it right or wrong. Now, why it works like that is because of our perspective. If you're north of the equator, if you have a northern latitude, it'll be what I have as a red diagram here. But if you're past the equator, so see right now how my celestial sphere, the red part is pointing up towards the North Pole. But if I was to head south, like what I have the second observer doing, it starts to tilt up. So now the North Celestial Sphere is in the ground, and the South Celestial Pole is pointing up. So as you continue towards Antarctica, that angle is going to get higher and higher. So for example, this December, when we go to Union Glacier Camp to do the final experiment, that blue South Celestial Pole will be about 80 degrees, almost straight up. So that kind of explains in the larger picture how everything works. As you're moving around our flat Earth, your celestial sphere will be rotating, and whichever pole is visible is where you're going to want to point your stick. So if you're in the northern area, you're going to want to point it to the north, and if you're in the south, you'll be pointing south. And what I mean by that is literally your compass. So see right here how my compass is pointing north? If you're in Australia, your stick will be going the opposite direction, facing south. And as you can probably see, it's quite obvious to tell why this works. You can literally see the sun is going to continue going. Oh, you can't see my mouse, sorry. But the sun will continue around that circle. Like literally that circle line you're looking at is literally its orbit. Throughout a day, it's not changing. Throughout the year, yes, the orbit goes closer and farther away from the north and south. Everyone knows that. But throughout the day, it's going to pretty much follow that circular path. And it makes this really, really easy to determine, at 12 o'clock, where will it be? And you can really measure this out quite easily. If you don't believe in this, you can use astronomy software such as Stellarium. It's free. Search on Google for Stellarium, but turn on the equatorial grid. You have to turn on the equatorial grid so that you'll see this exact same thing I'm talking about. When you're dealing with globe models, they will never show you the full 3D view. They don't want you to know the Earth is flat. So if you go to Stellarium, you're going to only be able to see something like this. You'll have your one perspective from the one observer, but they're never going to let you zoom out, and they will never show you two observers. If you have two observers, it's really easy to prove the Earth is flat. And if you can zoom out and actually see in like a 3D environment how everything works, it becomes even more obvious that the Earth is flat. But what I'm trying to say though is that you can use like astronomy software, and they will show you this view right here. It's called the equatorial grid, and they will project the flat Earth coordinates onto the sphere What they do though is they will pretend that we can see like beneath the land. So in globe software, they will show you stuff beneath it to try to confuse you. The main point I want you to be aware of is they will never let you actually zoom out and see the full 3D model. But to verify that what I'm saying is true, go to Stellarium, turn on the equatorial grid, and see where your north celestial sphere is. You can also just search for the star Polaris, and it'll be right there. And see how high it is. It'll be equal to your latitude. So if your latitude is 44 degrees, so you can check your GPS coordinates to figure this out. That is how high or low you're going to want to position your stick when you do this. And it's really cool because you can test this out yourself. This was the first photo I made at around 11 o'clock. And then at 12 o'clock, I got really excited because it actually worked. The shadow was completely under the stick. So then throughout the day, I'm now going to mark different areas off so I know when 6 o'clock will be, 2 o'clock will be. And there's math to do this as well that I'm going to want to go into probably in the comments. I'll show you guys how that can be done. But it's very easy. You just got a small stick like this even. You don't need to make it big like I did. Very small stick. Get a little protractor from the dollar store, compass from the dollar store, and you can start proving the Earth is flat.